Welcome to EDU World Space.
In problem 88, we have an object and a screen that's separated by a distance d, which I labeled uppercase D. And there is a converging lens that's placed between the object and the screen. So we have S here denoting the object to lens distance and S prime denoting the screen to lens distance. And we're asked to find the minimum distance between the object and the screen that will still give you an image on the screen. So I will solve this problem in two ways. The first way we'll use calculus, and the second way hopefully is a little bit more intuitive. So let's go ahead and use the equations that we know. And one of them we can readily use is equation 16, which will give us 1 over s plus 1 over s prime is equal to 1 over f. And we also know that d is equal to s plus s prime. So the goal in this approach is to find d in terms of just s and f, so we can kind of eliminate s prime, and then we can minimize d. We can take the derivative of d with respect to s, right, the one variable that we'll have, and then get an answer, and then set that equal to 0 and get an answer in terms of f. So let's solve this here for s prime. So you have 1 over s prime is equal to 1 over f minus 1 over s, which gives you that s prime is sf over s minus f. So now that we have this result, and we'll use this and also come back to it again later. So let's keep that in mind. So now let's substitute for s prime in this equation for d, right? And that's obvious from the figure. In the way the problem stated, we know that d is s plus s prime. So now I have d is equal to s plus sf minus s minus plus s minus f. And now I want to put everyone over a common denominator. So let me multiply the top and bottom of s by s minus f. So I have s minus f over s minus f times s plus sf over s minus f. And that gives me a d of s squared over s minus f. And now, so I have d as a function of s. And so I can take a derivative with respect to s and set that equal to 0. So let's do that on the next page. Right, so in the way you find an extremum, either a minimum maximum, in calculus that you take the first derivative and you set that equal to 0. So recall that we had d is s squared over s minus f. And now I'm going to take the derivative with respect to s and then set that equal to 0. So the derivative of d, I'm going to take the derivative of this guy. Let me write that right away. So d by ds, and I'm going to substitute this for d, s squared over s minus f. And when you take this derivative, you will get s times s minus f over s minus f squared. And we have to set that equal to 0. Right, so we don't want anything. So how will you find the roots or the s value that will satisfy this equation? So if you look at the numerator, obviously one solution is s equals to 0. If s equals to 0, then this whole expression is 0. Another solution will be s. Oh, I think I made a mistake. That should be 2f up there. Apologies. Let me write 2f minus 2f. Okay. Yeah. And another one is s is equal to 2f, right? Well, s is equal to 0, we will discard the solution because when you're inside the focal length here at s equal to 0, your object is right at the vertex of the lens. This will not give you an image that's going to be to the right of the lens, right? So we will discard the solution and we will choose this one to be our solution here. But remember, the goal is to find d. Okay, so now remember that d is equal to s plus s prime. Well, we know s, but we don't know s prime. But recall before we had found this expression for s prime. So s prime is sf over s minus f. And let's substitute 2f for s, 2f minus f. And that gives me a 2f. So then d is 2f, which is s, plus 2f, which is s prime. That's 4f. And there we have our minimum distance. Now, there, like I said, there was another way to solve this problem. And in this other approach is, again, to use the same two equations that I had, equation 34.16, and the fact that d is equal to s plus s prime. So from 34.16, you have 1 over s plus 1 over s prime is equal to 1 over f. And now we will substitute for s prime from this equation. So s prime is d minus s. So 1 over s plus 1 over d, d minus s is equal to 1 over f. And now let's put the left side over a common denominator. So then we'll have d minus s over d minus s times 1 over s plus 1 over d minus s. And that's equal to 1 over f. And this side, I have to multiply by s over s, which I forgot there. Okay. So now I have d minus s plus s over ds minus s squared. That's equal to 1 over f. And let me cross multiply. So right away, these two terms cancel out. So then I have df is equal to ds minus s squared. I'll take all the stuff on the right-hand side and put it on the left-hand side. So I have s squared minus ds plus df is equal to 0. And now I have a quadratic equation, which I will solve for s. So s is equal to d plus or minus square root d squared minus 4df, all divided by 2. Now, the important bit here is basically what's happening under the square root. So we want to determine what value of d will still give us an image, right? So to the right of where the screen is. So we need to figure out what's going on with d in terms of f. And so if we look at the square root, so we have square root of d squared minus 4df, which I can rewrite as square root of d. I'm going to factor out a d, right? So that leaves me d minus 4f. Okay, now If D is less than 4F, then the square root is imaginary, and then S becomes imaginary, and we haven't encountered anything like that explicitly, so that can't be a solution to our problem here, right? So we'll discard that. So D cannot be less than 4F. Okay. So what happens is D in this case can be equal to 4F, right? And that will for sure give us the minimum. If D cannot be less than 4F, but D can be itself 4F, then that's for sure the minimum. Because otherwise, then D is greater than 4F. So there we have found the minimum distance.